afternoon, grade 12s, or math history. I have given you guys, I should have already spent about 10 minutes or so working away through this investigation. So the first page I'm just going to go through and lay out the answers to it. The second page, though, we're going to fill in together, so it'll take a little bit more time here. But basically, we have 5 students, Al, Byron, Colin, Dave, Eric. They take part in a cross-country race to represent their school. We have the winner gets $50, runner-up gets $25, and third place winner gets 10. So there's different first, second, third position are awarded, and it's very different what each position is. So we have a table here that shows all the possible combinations from those 5 people. Basically, what we have is the number of ways there are of picking 3 people, or groups of 3 from 5. That's what we have here in terms of the solution. So it says how many ways are there to award the 3 prizes? We get 60 ways. Okay, we count these all up, there's 60 ways. So I already showed you up here that we could do it with the permutation formula. It can also be done with the fundamental counting principle, right? This is going to be first place, second place, and third place. There's 5 ways to fill first place, then 4 ways to fill second place, and 3 ways to fill third place. Because once a person's been awarded first place, they can't be given second place or third place. And that again gives you 60 ways. So we want to pay attention to the fact that there's a difference between first, second, and third place. That actually, something different happens for each of those places. The second part, part B, is just says, for participating in a cross-country race, the school's been awarded 3 places at a running clinic. So these are the same thing. So these 3 places are all the same thing. So those 3 places are all the same thing. And that means that ABC is the same as CAB is the same as BAC, and so on. So the school coach decides to select the 3 lucky students from the ones who took place in the cross-country race. Use the table above to circle the different ways that 3 students could be chosen. So what we have is that all of these choices here that all contain A, B, and C, they would all amount to the same 3 people going to that clinic. So they're all the same combination. So we just need the top one, and that's true of each column because of the way that this question has been laid out, to be that to have all of the combinations that involve the same 3 people listed in each column. So what we end up happening there is instead of 60, we've got 1, 2, 3, 4, 5, 6, 7, 8, and we've got 10. 10 ways. So how many ways are there to select the 3 students? We have 10 ways. And this isn't anything that we could have gotten from the fundamental counting principle, like laying out the lines, or from the permutation formula. What we have is a different kind of formula here because we need a way to eliminate those the 5 extra ways for each of the 10 ways. Right? Each of those 10 ways had 6 different ways that they could be laid out if order was important. We don't care about order. We need to divide out 6 ways each time. So we have to divide out some sort of number sometimes. So what we have here then is the difference between, or what that investigation was supposed to do was illustrate the difference between what is called a permutation, which is the number of ways of arranging n objects in groups of R, where the order of the objects is important, and a combination, which is the same thing, the number of ways of arranging n objects in groups of R, but it's where order is not important. So that means where you have a whole bunch of combinations that represent the same thing. So in terms of a permutation, we have our formula that we've already learned how to do that. You can either use the fundamental counting principle, so that's the lines, okay? Or you can use the formula n pick r, which is equal to n factorial divided by n minus r factorial. I'm not going to quite give you the formula for combinations because that's going to come on the next page as part of the notes. This is a separate page here. When the order is not important, so if the order is not important, then that means you have to divide out the repeating combinations, the combinations that repeat. But the combinations that repeat, you can also think of it as the combinations that mean the same thing, that repeat or contain the same objects. or a really good example of combinations is card hands. Because it doesn't matter what order you put the cards in your hand in, whatever cards you have, that's your hand. It doesn't matter if you put the jack first or the king first or the one or the ace first. Another way to think about this, like a permutation, it's like committees with positions. So, like student council has a president, vice president, secretary, treasurer. That would be a permutation. Just a group of students, like you're just gonna like the grad committee. That would be a combination. So committees with positions, so like i.e. student council. And a combination would be committees without positions. Like the grad committee. So I think I kind of already gave away the next part here. Is just which part of the investigation on the previous page, A or B, is a permutation. Explain which part's a combination. So the permutation is A, or A, because you had first, second, and third were different. And the combination is part B, because the place in the clinic is the same for everyone. Another thing to keep in mind is permutations will always be a larger number. Combinations will always be a smaller number. Because you're in the combination formula, inherent in the formula is dividing out the repeating combinations. So the number of combinations is equal to the number of permutations divided by R. Sorry, R is here, like specifically divided by 6, and put there 6, which is the same thing as 3 factorial. So what you're dividing out by again is R factorial. You can R factorial out there. But let's if we go to the formula on the next page. So now you're in your notes booklet. I need you in your notes booklet, and you're going to be on page 22 in your notes booklet for the definition of the formula. Okay, so we want to remember this again is n different elements taken R at a time. So it's the same thing as a permutation. Again, it's just that you're just saying that some of the combinations don't matter because they're the same as a different combination you're counting. So order is not important. And probably one of this then brings up one of the hardest things about this unit is when you get a question in front of you is trying to determine, is it a permutation or is it a combination? So is order important or is order not important? And a lot of those decisions just require logical reasoning about things that we are aware of in the world around us. So the formula for combination, and this is on your formula sheet, is N choose R, so NCR, and that equals, it's similar to the permutation formula, but we have to divide out an extra number. So we're going to divide by n minus r factorial, so that's the permutation formula. But then we also divide out r factorial. This is, like I said, on your formula sheet. And we say n choose r, whereas a permutation was n pick r. It is on your calculator under, you're going to put in whatever number you have for n, then math, probability, and then it's 3. And then you type in your value for r, and then you hit enter. There's another format this formula that's also on your formula sheet. And what's on there, it says that N choose R can also be written as N over R in brackets without a division symbol. That just means the exact same thing. It's just a shorthand way of writing a combination. So it's also on your formula sheet. So just to illustrate this here, if you've got, if you have something that looks like this, 16 and 7, and then in brackets, that just means 16 choose 7. Okay, so we'll try an example to see how this works, and I'll try to explain in the example why it is that this would be a combination. It's not immediately obvious. So we have 6 students from a class of 10 are to be chosen to go on a school trip, and how many ways can they be selected? So they're just going on a school trip. This is like saying 6 out of 10 of you are going to go on international travel. All the positions on international travel are the same. You know, if Chase, Lane, and Brad are chosen, that's the same thing as Lane, Chase, Brad, as Brad, Chase, Lane, that kind of thing. Those are all the same. So we don't count those combinations twice. So order is not important, so this is a combination, which obviously it will be because that's the lesson we're doing. N is the total number we're picking from, which is 10, and R is the number, the group size that we want, so 6. So we want 10, choose 6, which you can calculate on your calculator. What that actually means, and I'm only going to write this down once because it just ends up getting kind of confusing, but this is another way you can calculate it. You can use the 10, then go math probability 3, 6, enter, and get it that way. You can also use the definition of that formula. So 10 choose 6 is 10 factorial divided by 10 minus 6 factorial times 6 factorial, and you can calculate it that way. If you put that into your calculator, then you just need the big red brackets there. You don't need any other brackets in there. And the answer to this would be 210. But don't feel that you need to write down the expanded version every single time. It's sufficient, and you'll see in the next question, I'll show you what you need to show. If you're just going to use the 10 choose 6 formula on your calculator, then there's no need to write out 10 factorial and so on. So a really good example of something, this is going to come up again in probability because we're talking about, is how many different ways there are of playing Lotto 649. Okay? So to win Lotto 649, a person must correctly select 6 numbers between 1 and 49. Jasper selected the 6 numbers for the birthdays of his family, so he picked 3, 7, 9, 11, 20, 29. And how many different selections of numbers could have been made? So how many possibilities are there? And then that relates to probability, because then the probability of winning is your one ticket divided by the total number of possibilities. And order doesn't matter here because it doesn't matter what order these numbers are in, it's still those same 6 numbers. They come out of the machine that picks the 649 numbers randomly, but then they're always put in ascending order afterwards. But it doesn't matter what order they actually come out because those 6 numbers are those 6 numbers no matter which order they come in. So with Lotto 649, your N is 49 numbers, and your picking number, you're choosing them in groups of 6. So you have 49, choose 6. So you know 49, math, probability 3, 6, enter, and you get that there are just about 14 million combinations. So that means to win Lotto 649, you have a 1 in 14 million chance of winning. So you'd have to buy 14 million tickets to guarantee a win, which is huge. Okay, next page, I believe, is a question for you guys to try. So you can pause the video here at this point if you want, or you can just kind of carry on. So how many different 4-topping pizzas can be made if there are 9 different toppings available? So I'm going to assume you paused a little bit, and I'm writing the answer out here, but you should know how to do it. Okay. So example 3. The restaurant serves 10 flavors of ice cream. Danielle has ordered a large sundae with 3 scoops of ice cream. How many different ice cream combinations does Danielle have to choose from if she wants each scoop to be a different flavor? So the assumption that you're making here is that if you've got like chocolate, vanilla, strawberry, that's the same thing as strawberry, chocolate, vanilla. The same thing as vanilla, chocolate, strawberry, and so on. That a sundae with those 3 flavors is the sundae with those three flavors, no matter what order the scoops come in the tray that you get them in. So our N here is 10. And we're choosing groups of 3. So we have 10, choose 3. So 10, math, probability 3, then 3 again, and that's going to give you 120. So the your turn question for you to try here is the same situation, however we have a restriction. If one scoop in our large sundae must be chocolate and the other two must be different flavors, how many combinations of ice cream are possible? So when you're dealing with your restriction, so initially we had, just like I thought, I'm hoping again you guys pause this to actually calculate this before carrying on. We're picking 3 scoops of ice cream, but we're told that the first scoop, not the first scoop, but chocolate has to be in there. So that means we're going to remove chocolate from the choice of 10, and that means she only has 2 scoops that she can randomly fill in different ways. So that means 9 choose 2, or 36. So I just got to do my notes. Okay, next page. We'll start looking at slightly more complicated questions, or ones where we have to do a little bit more thinking, and maybe we have to calculate more than one number. Okay, so we have here, the athletic council decides to form a subcommittee of 7 council members to look at how funds raised should be spent on sports activities in the school. There are a total of 15 athletic council members, 9 males and 6 females. The subcommittee must include exactly 3 females. To determine the number of ways of selecting the subcommittee, if there are no further restrictions, and then we're going to say if we have to include Bruce, the football coach. So, we have to look at what we have here. We have 15 total. Okay, so in total, N is equal to 15, and we want a committee of 7. 7 council members. The problem here is we want to specify the genders of the people or specific people on that committee. So then we actually, this isn't good enough. This isn't specific enough. So we have to look at males and females. So the males, we're told there are 9 males and there are 6 females. And the only other information we have is that the subcommittee must contain exactly 3 females. So that means we want 3 females, and then we have to figure out if we want a committee of 7, how many boys does that, or how many males does that mean that we want? And what you should notice here is that 9 plus 6 equals 15, and then we've got 3, and whatever we put in here for R, when it's added to 3, it has to give us 7. Because we need to have 7 total on our committee, and we need to be choosing from a total of 15. So your individual N's, when you break that up, they should add your total N, and your individual R should add your total N. And then what we have to do is we need to recognize that this is the word and. We want males and females on the committee, so that means we're going to multiply. Now, I did actually kind of write this down backwards. It's actually the females that I wanted to do first. So we have 6 choose 3 for the females. And for the males, we have 9 choose 4. And then we're going to multiply those together. Okay, because for all of the ways there are of choosing 3 females, there's that number of ways of choosing 4 males. So what we get here is 6 choose 3 is 20, and 9 choose 4 is 126. So then we multiply those two numbers together, and that gives us 2,520 different ways of doing that. The way that I labeled this, I'm not happy with it. I'm just going to change this. I'm going to try and keep it consistent. Although I said that you can't really do the lines in the way we did with the fundamental counting principle with combinations, but really you can think of it that this is the number of females and this is the number of males, and you're combining it. So once you determine that it's a combination, that's the formula you're going to use in situations where you have multiple different combination formulas to use, you consider the use of those formulas as the fundamental counting principle. So you're going back. So this is the number of permutations this may become, if that makes sense. In the second half, B, we want Bruce, the football coach, must be included. So we're going to go back, and I'm just going to approach this one in a slightly different way, but it does the same thing. So we need to have Bruce, and we need to have the females, and we need to have the males. And what I want you to remember is that all of the n's need to add to the total n, and all of the r's need to add to the total r. So we should still be getting a total n of 15 and a total r of 7. So for Bruce, there's only one way of choosing Bruce. One Bruce. We're choosing one Bruce from one Bruce. For females, we're still sticking with exactly 3. So we have 6, choose 3. The males now, though, we initially had 4 males that we were choosing from 9, but one of those males has to be Bruce. So we have to take 1 away from the 9, which gives us 8 males left, and 1 away from the 4, so we're choosing 3. Because Bruce has to be on there. So it's those 3 combinations is what we're determining, or using to determine how many total ways there are to fill in this committee that has to have 3 females, and Bruce is one of the males. So there's only one choose one. There's only one way of choosing Bruce from one Bruce. 6 choose 3 we did. That was 20 already. And then 8 choose 3. It's going to be just a little bit less than 126. So we should get 56. So the total number of ways of forming the committee that way is 1,120. So at this point, I'd like to ask you to complete the your turn question there, which is similar. Just looking at a basketball coach, we've got 5 guards and 7 forwards on his basketball team, which is a total of 12. And so just the number of ways he can select a starting team of 2 guards and 3 forwards, and how many ways there are if the star player, who's a guard, has to be included. So exceptionally similar to the one that we just did. So if you need to pause this while you're here, please do that. I'm just going to write the answers down here. So 350 for part A and 140 for part B. If you didn't get those answers, take a couple minutes to try and figure out what you did wrong. And maybe compare with somebody sitting close to you to see if they can help you through what you might have done wrong in that particular question. So then the last thing that I want to talk about here are questions that are typically, like, they involve the words at least or at most, no more than, no less than. So this is a standard of excellence outcome. Okay? Because what you're dealing with here is you're not dealing with exact numbers, which makes these questions a lot more challenging to complete. So again, you're not going to encounter a lot of these because they are standard of excellence. They're a little bit tougher. Do expect some on my exam, and there's plenty to practice in the practice questions that I'm leaving you guys to do. So there's 2 ways you can answer these questions, and it's what you need to get good at, and why this becomes a standard of excellence question is if you're not careful, you can end up doing a significantly large amount of work when you could have chosen to approach the question from a slightly different way and done a lot less work. So I'm going to show you the 2 different ways of approaching a question like this, and what you have to look for to determine which way to do it. One is going to be using what's called direct reasoning, and the other one is called using indirect reasoning, which means you're just approaching it from the back-end way. So we have a planning committee is to be formed for a school-wide Earth Day program. There are 13 volunteers, 8 teachers, and 5 students. How many ways can the principal choose a 4-person committee that has at least 1 teacher? So at least 1 teacher. Okay, at least 1 teacher means 1 teacher, or 2 teachers, or 3 teachers, or 4 teachers. And remember, those ors mean addition. So this means you have to figure out 4 different combination statements and add them all together. And within those combination statements are the fact that we need teachers and students. So we need a certain number of teachers, certain number of students. So if we're making 4-person committees, and we have 1 teacher, that means we're going to have 3 students. If we're going to have 2 teachers, that means 2 students. 3 teachers, that means 1 student. 4 teachers, that means no students. So then we have to figure out number of teachers and number of students for each individual expression. So notice that this is 4 separate multiplication calculations that we then have to add together. There's a lot of room to make mistakes. So this is teacher, student, teacher, student, student. have 8 teachers, we're choosing 1. 3 students, we're 5 students, we're choosing 3. 2 teachers, so 8 teachers, so 8 choose 2. 2 students, so 5 choose 2. 3 teachers, so 8 choose 3. 5 choose 1 for 1 student. And for teachers here, we have 8 choose 4, and we have 5 choose 0, which we don't need to calculate. That's always equal to 1. There's only one way to choose no students from 5 students. A couple things also. Whenever you have any number choose 1, that's always going to be equal to that number. Then the other ones we just have to calculate. And just because I'm running out of time here before my next class starts, I'm going to fill in the numbers here. So 5 choose 3 is 10. 8 choose 2 is 28. 5 choose 2 is also 10. Notice that. Okay? If you can get the same number from two different, we have the same n's, but 2 different r's, we get the same number. That's just a pattern to recognize. 8 choose 3 is 56. 5 choose 1 is 5. And 8 choose 4 is 7. So this gives us 80 plus 280 plus 280 plus 70, which gives us a total of 710 ways. So that was a lot of work. And with these, at least at most questions, if you choose the portion of the question that has less in it, you can do a little bit less work. So this way we did direct reasoning. So we just added up the different number of ways that we're getting of getting at least one teacher on the committee. Indirect reasoning means you're going to take the fact that you can figure out the total number of committees. So what you're doing is you're using the complement. You're using the complement. So you're going to take the total number of committees that's going to be equal to the number of committees. It's a long word to spell. Number of committees with at least one teacher plus the number of committees. The complement of at least one teacher is with no teachers. No teachers. So the total number of committees is the total number of people we have, which is 13. Choose the number of people we want on the committee, which is 4. And that's going to be equal to the number of committees with at least one teacher. That's what we're looking for. So I'm going to put an x in there as a variable because that's our unknown that we want to solve for. And then we're going to add in the number of committees with no teachers. So that means if we have teachers and we have students, we have 8 teachers, so 8 choose 0, and we're going to have 5 choose 4. So 13 choose 4 gives us 715, and then we have x, and the number of ways of getting a committee with getting a 4-person committee out of 5 students, 5 choose 4, this is equal to 1 times 5. So our x is equal to the total number of committees, which is 715, minus off the number of ways of getting a committee with no teacher on it. And that gives us the same answer. But it was a lot less work. It just requires a little bit more logical reasoning to think your way through. So there's a your turn question for you guys to try here. And so then just give yourself some time to work on this, and I will give you the answer momentarily. I got to change some numbers in here. We've got a 5-person, 5-alderman committee. And we want at least one female, but we can't take away all males because there's no way of making a committee with no males. So let's actually just omit this question. This was just a bad one. So we'll just get rid of that one. There'll be some in your package that I'm going to give you, the questions that you can work on, that you can complete. And then we can also, I'll go over some more of these with you on Tuesday when we're back. And we're doing our sort of our review part of this. So questions you can work on. It's your choice in terms of how you're feeling about stuff, which of these you want to do. Okay. So to practice is more with combinations. So just combination practice. So combinations only. And you may just want to look for questions like that last example we did and the your turn question that I had to omit here. So these are all from the text. Okay, so page 118 to 120. Question numbers 4 through 18. For all counting methods, okay, and these are in random order, okay, so that it's not laid out in the way that it was laid out in the notes. It's in random order so that you can kind of practice picking what's a combination, what's a permutation, and if it's a permutation, which one to use. So looking at page 126 to 127, numbers 4 to 16. Okay, so work on those. And as I said, on Tuesday, when you're back after your nice 4-day long weekend, we're going to be looking at, we're just going to do a bunch of different counting problems and solve them, and we're just going to practice how to determine whether it's a combination, whether it's a permutation. But I'd like you to get a head start on practicing some of the ones from the textbook. Okay, thank you guys, and have an excellent long weekend.